Oh no, there is only one queen. Okay, we're done. A lot of this is rehashing material we already kind of saw, which is okay. I'll slow down a little bit, but we're gonna see. I really wish I had. Yeah. We're gonna actually take a look at linear momentum. Yeah, oh my God, it's killing me. But we're going to take a look at linear momentum. When we get to rotation, we're going to look at rotational momentum. A little bit of foreshadowing and spoilers. When we get to rotation, we're going to see rotational everything. We're going to see rotational kinematics. We're going to see rotational dynamics. We're going to see some rotational energy. We're going to see some rotational momentum. We're going to see rotational versions of everybody. So that's usually why we do it at the end as kind of a review of like, hey, here's everything that we saw this year, and this is what happens when we put it in a blender. Kind of, yeah, in most cases. Here's what happens when you do this with it. Woo, around and around. Linear momentum describes motion in which the center of mass, and this is going to be annoying, because I use COM for something else as well. Lowercase COM means center of mass of an object or system changes position. Very similar to kinematics. Very, very similar. Anytime the center of mass changes its position, we say that it's in linear or translational motion. They mean the same thing. The reason why I'm bringing this in here again is kind of foreshadowing the fact that we're getting closer and closer to that rotational type of motion where the center of mass actually does not change position. It's going to stay where it is, and everybody else is going to move around it. We're going to get to this guy in a little bit. It's not its time yet. So very briefly, we're going to just talk about the center of mass. We're going to actually, give it its full attention when we get to gravitation, which is next. But so we have an idea of what it really is. The center of mass of an object or a system is the point around which the mass of the object is evenly distributed. Think of it as the balance point or the center point.
Do you guys remember in geometry when the centroid?
In a uniformly distributed system, the geometric center, the centroid, is the center of mass in a uniformly distributed system. In a non-uniformly distributed system, that no longer works, but we'll deal with that when we get to it. That's okay. That's not a big deal. But we already said this line. I said it again, but it's not that big a deal.
What about the vertical line?
There is a vertical line. It becomes important a little bit later that goes through the center of mass where the system balances.
Can you use an object?
So, no.
There's a trick to do.
Yeah, there is. You start at both ends and you go through the middle, but I'm not about to do that. And I'm close enough right about there that I'm pretty happy with it, more or less. So there's a vertical line right through here, right? So that cuts it right in half. And the center of mass of this object lies somewhere on this on this vertical line this way. It actually just happens to lie right there on the object. Right here. Sorry, you can't see it because I'm pointing the wrong. You're pointing the wrong way.
So the vertical line is determined by that point.
Yeah.
It's not the vertical line is its own thing.
Not yet. Not yet. We're going to actually compute center of masses in another chapter. We're going to compute them through mass distributions, and we're going to compute them for discrete distributions. Well, I'm sorry, let me say this another way. We're going to compute them for continuous distributions and for discrete distributions later. A continuous distribution will require an integral, and a discrete distribution might not. A continuous distribution is exactly what it says, just like a continuous function has no abrupt stoppages or changes or shifts, right? It just keeps flowing. A continuous distribution of mass is one where there's suddenly there's no point where there's suddenly no mass. Your body is a continuous distribution of mass. You're not just going to suddenly find a point and go, oh, there's no mass there. If there is your body there, then there is mass there. So a couple important details about momentum that we've already talked about, but I'm just going to say it again. It is a vector quantity. That's actually really important. We got to have either the bold or the arrow, and I did both. I believe in double dipping, like I do. That's why I always have my own dipping sauce. I double dip everything. Double dip everything. Momentum gets its vector property, its vector nature. Whoops. Momentum gets its vector nature from velocity. So the momentum vector will point in the direction of the velocity vector. We're going to get to that in a couple of slides. Energy is a scalar quantity. But it has velocity squared. That's the important part. And when you take a vector and you multiply it by itself, that's actually the dot product of a vector with itself, which is a scalar. Work is also a scalar, but it's allowed to have signage because the signage there, because work is force dot delta x, and that dot product, again, produces. Then the other name, does everybody remember the other name for a dot product? I said it very briefly. The other name for a dot product is called a scalar product. And the reason why it's called a scalar product is because it produces a scalar. The units of momentum are, taking a look at this, where'd you go? Cotton Eye Joe. There we go. The units of momentum, taking a look at this equation, should be the same as the units of mass, which are what? Unfortunately, there is no reduced unit for the kilogram. One year, my first year, the students wanted to call it an aerial. Don't do that. Please don't do that. That's my first name. Don't do that. Since momentum is a vector, it must have a direction. We've already touched on this a little bit. We already know most of this. The negative signs denote positive or negative denotes moving right, left, up, down in the one-dimensional world. If we're dealing with a 2D vector, we would use what? We have a direction, right? Because it's a vector. If we use positive and negatives, we're talking about a 1D vector, right? How would we talk about a 2D vector? We could use vector notation. That could work. There's another way we could do it as well. What's the most common way that we have denoted a two-dimensional vector before? What two pieces of information have we usually been given? The angle. Either with vector notation or with an angle. We can visually represent the momentum the same way that we represented velocity, using an arrow. They'll point in the same direction, but the momentum vector is going to be a magnitude of m larger, or smaller, depending on what m is, right?
Can you say that momentum is the antiderivative of, or the derivative, can you say the force is the derivative of momentum? Because force is mass times acceleration, and acceleration is the derivative of velocity.
Mathematically, you would probably get the same thing, but they are not the same thing. Because if you take ma and you take the integral of ma, right? Yeah, you take the integral of ma, you would end up getting mv, right? But the integral of f is not necessarily p. Not necessarily.
Okay. How can
They don't represent the same thing. They don't mean the same thing. Just because something mathematically can point to the same place doesn't mean they actually are the same thing.
The derivative of energy is momentum. Kinetic energy.
Oh, shoot, it is.
No, not exactly. There is a relationship between momentum and energy, kinetic energy. It's not a derivative relationship per se. The units work out really well, and it's a tricky one. It really is, because it makes you want to think that, right? Because if I take the derivative of 1/2 mv squared, I get right into mv, right? Don't do that. Don't think that, because they're not. It's not exactly that way. We'll figure that out. We already kind of started this a little bit better yesterday, but Gabby missed it, so I want to redo it a little bit. Newton actually started, and I know you guys already did it, so I'm going to do it a little quicker. Newton wrote his second law not like this, but using, actually I'm going to write it, oh wow, I even said T in my head and then I just didn't do it. You guys remember that we did this on the board yesterday?
Yes.
Where's your notebook, dude?
I lost it.
Rip in peace, bro.
Put it into your bag.
Rip
Yeah, I know, but I
in.
lost
How, man?
You said it. They need like some like with the tracker. Did you get a tracker?
That's a good idea. You should make yourself like a little cubby in there.
We have like.
I don't
There's a
get it.
copy right here, Dad.
No, don't do that. Someone else will take it. But like, it just your bag, man. Your bag. Like, I just,
Yeah, it was there.
if I manipulate this thing algebraically, I multiply this by delta t, and I kind of pull out that delta a little bit, common multiple rule. I can rewrite Newton's second law, F equals ma, in terms of
Wait, why are you using this? Why are you
there's not a main reason. There really isn't. I'm going to change my notes. In terms of impulses, which is a force applied over a time interval, and changes in momentum. So Newton actually originally wrote his second law not in terms of forces and accelerations, but in terms of impulses that cause changes in momentum. An impulse, I did not want that actually pointing at me. An impulse is a force that is acting on a system that changes the system, but that's on it over a period of time. Now we use, I don't like green, the letter J. Yeah, I don't like that at all. I hate this so much. It just keeps going back and forth between me and the video, and me and the video, and me, and I just, or the board. I don't like it. I really don't. I'm just gonna go ahead and put that right there. That's what I'm gonna do. Right there. That's all I'm gonna do.
How it's supposed to work?
Ideally, yes, but
But right now it's really
right now I don't really need it to do that. Tiny intervals, and yet it's going. It's like a tennis match. So we use capital letter J to represent impulse. So using this definition, an impulse is an amount of force applied over a time interval. That's what an impulse is. It's totally cool. Totally cool for us.
So the impulse is the same thing as momentum?
Not momentum.
The change in momentum?
It is the same thing as a change in momentum. Or we can say that is also equal to the right-hand side of the previous equation, that an impulse is equal to the change in momentum. And they're both the same. And these are really, really useful because it lets me relate velocities, impulses, and forces. Oh, and time all together. And sometimes we'll get these different variables at different times.
Oh, I get it.
We've got an AP question. This one has more than one correct.
You're wrong.
That's a British West by energy.
Identical kinetic energies. Maybe.
We college board is British.
I don't know.
Spelling things British for me.
I don't know, man. I don't know, man. I'm given a college board resource, and that's what I got, man.
Yeah, but
No, it's Afghanistan.
of different masses, but identical kinetic energies. They missed that.
Probably. I don't know. I'm giving them an out, man. Let me give them an out.
Even the dot is spaced a little further.
Yeah.
So, for multiple correct, I need to get them both in order to get full credit. There is no partial credit.
Multiple correct is always 2.
Yes. Consider 2 laboratory carts of different masses, but identical kinetic energy. Which of the following statements must be correct? Select 2. The one with the greatest mass has the greatest momentum. Let's take a second. Let's write out kinetic energy. Let's write out momentum and see what happens. What is kinetic energy?
1/2 mc².
So if I think about this in terms of cart 1, and I think about its kinetic energies, both of their kinetic energies have to be equal.
Are we assuming that like cart 1 is heavier?
We can pick whichever one you want, okay? Cart 1, let's say this one is heavier.
But since one has, because they have different masses.
They have different masses, so one has
Right,
to
so
have
the
a...
velocity
Okay,
in
well,
one of
we'll
them.
pick one. So in terms of their kinetic energies, if cart 1 is heavier, then it has to be going
Slower.
slower. Has to be going slower. The question though is, how much slower?
Yeah, it has to be
Square
going
root of
a lot,
the change
like,
in that.
yeah. Because this one's square root, so then
Yeah.
it has to be going,
Square root
Because
of
the
the
kinetic
change.
energy is squared,
yeah. Not square root.
right? The velocity piece squared, it's a quadratic relation. That difference in velocity
It's
is really big. Like it's a really big deal. Okay, so one has to be slower, but how much slower? We've got to think about it. Momentum.
Well, you can't answer that without knowing how much heavier the other one
No,
is.
well we can think about it. We can think about trends. Momentum is what?
Mass and velocity.
mv. Okay.
The first one is false.
Why?
Because the one that's heavier, the velocity is a lot slower. So even though the other one's lighter, since the velocity is going to be a lot bigger, that makes sense.
Okay. Does anybody else agree with that?
Yeah,
You agree with that?
I do.
Okay.
Like,
Because
it's tough because you don't have like how different they are though.
Right.
Because
That's
it
true.
would be because
right, it depends. I guess, but-
Well, let's go through and see what else we can get. Maybe it'll be easier. Let's go to B. The same impulse was required to accelerate each car from rest.
impulse, which is
Impulse. Okay, well let's look at impulse.
V delta, the change in
Impulse
momentum.
was
Force times change in or the change.
or
Change
the
in-
change. Whoops, that's a terrible delta in momentum. So then if they both started from rest, so that's good. They both started at 0. So their change in momentum is really going to end up being whatever their momentum is at that point. Does that make sense?
Which is the same as
So that kind of leads me right back to A a little bit.
Yeah.
Okay,
So either it's
C.
Either it's B and D or it's A and C. Those are kind of the only two choices. B and D kind of they rely on
Yeah.
each other. Like if B is true, then B must be true. So either they're both false
Why?
or both.
Why is that true?
Because
Because the same amount of force was required to accelerate both cars from S, right? And the same impulse, and the impulse is like delta F.
So you said B and D?
B and D. Yeah, B and D.
Okay.
Like,
Well,
so
let's
they
keep
both
going.
have like a.
Wait, what is he saying?
Let's keep going. Let's finish reading the options.
Alright.
See, both can do the same amount of work as they come to a stop.
That makes sense.
Why? What does that make sense?
Because if they have the same kinetic energy, then they should require the same amount of work.
Work
Why?
is also change in energy. So if they have the same energy, it's gonna require.
So we
the
said
same.
work was change in what kind of energy does this
Kinetic.
have? Okay, change in kinetic energy. We both know we know that for sure they have the same kinetic. If they stop, they'll both have the same final.
Right.
So
then it has to be the
So it
same.
has to be C. I like that. Okay, for sure it has to be C. C is definitely a good option.
Yeah.
Okay. And then D. The same amount of force was required to accelerate each car from rest.
No, the masses are different.
Well,
Right.
In the velocities
Why?
No,
Why?
but the work.
Well,
No,
it's not
F
telling
equals
you.
MA. Just think about it, F equals MA.
Okay. What does F equal
Right,
MA
but-
tell me?
If one M is higher, then the other F has to be greater.
But that's
But
only
that
if you
doesn't
want an
affect-
equal. If you want it to be.
If I want, yeah,
if
that's
you want it
true.
equal.
They don't. They're
They
not
don't have
at
to
the
be
same
equal.
velocity.
Right.
I don't need them to be at the
based on
same
the assu- What
velocity.
you're saying is that they're going to stop at the same exact point,
Right. But you don't have
but
to.
you don't have to.
First of all, D doesn't say anything about them stopping.
Right. But it doesn't matter about stopping.
It's about them starting.
Right. But it doesn't matter if one goes faster than the other because it doesn't say that that's a condition.
In fact, actually, I know for sure one of them has to be
They can't-
faster
yeah,
than
they
the
can't
other.
be the
Right.
same
For sure.
So,
Like
you
I
would-
know for sure.
Yeah, because when they're different, that doesn't have the same kinetic energy.
Right.
I know for sure the velocity of one has to be much smaller than
That
velocity
one
of two.
would make sense.
I know for sure.
Because if you're starting in with the same force.
Is that much?
The velocity of one is much smaller than two.
How do you double less than?
Yeah. You guys you don't use that notation in math?
I've never seen that
Oh,
before.
we use that notation in physics.
Never seen that ever.
Oh. That's usually when you say it's much smaller than something.
Because much is a
Wrong.
judgment call, so we would
Oh.
mathematically.
No, we're very judgy. Right, we really are. But so V1 is much smaller than V2. So we know that for sure. So I don't need the two forces. I don't need the accelerations to be the same. I definitely don't.
And making sure that the same force was applied ensures that one of them is going to be going a lot faster.
Okay. So do you agree with D?
I think
Same.
What's the difference between B and D? What's the difference?
B and C.
Same
Oh,
impulse.
they're
Impulse,
related.
one
to
has
time.
time.
Impulse has time. So they both have the same amount of. They both
Take the
were
same amount of time.
accelerated for the same amount of time,
Right.
right? But what that also means, if they have the same impulse, what else does that mean?
They have the same momentum.
No. Well, okay, hold on.
Change in-
Let-
in
They have the
same-
same. That's
in
farther
momentum.
down. They have the
The
same
same
change in momentum, right? If they have the same impulse, then they have the same change in momentum.
Yeah.
But they started from rest.
So you know that
So they started from zero.
You have to have the same impulse.
So that wouldn't make sense.
Why not? Why would that not
Because
start
if
from
They're
rest?
both starting from rest and they have the same change in momentum. That means that, wait, let me.
Yeah.
Okay.
because
if,
then if you can have the same momentum.
in order to have the same change in momentum, and you already know that one of them is the same, the other one has to be the same too. If not, it's not going to be the same.
You said the same 5 times in
Yeah.
that sentence.
Okay. If you already know that their initial momentum was 0, in order for the change in momentum to be the same in both, the final had to also
Momentum
be the
has to be
same.
the same.
The final momentums have to be the same.
And they're not.
They
And
could
they're
be.
not.
They
Yeah.
could be the
They're
same.
different velocities though.
But
The
You
time
also have to
doesn't.
hear math.
They
The
wouldn't
issue-
make sure in the same time.
Because you know that if m
Well, yeah.
if mv squared is if
Equal.
each of the kinetic energies are equal, then you know that it's then velocity is multiplied by the square root of m.
if MV squareds are the same, forget the 1/2 for a second. If the MV squareds are the same,
There's no way
can the
about
MVs be the same?
No.
Possible.
Well, except for in certain very certain situations.
like 1,
One.
right?
Zero.
Are there any
No,
other
but it couldn't
cases
be-
except
but it
1
couldn't
and
be
0?
one either way because the masses.
What? Is there any other mathematical cases? I can't think of any other mathematical
It
cases
can't be
except
because
1
the masses.
And 0.
The
where
masses are different.
mv squared would be the same as mv.
V squared.
No,
No, but the masses are different.
Oh yeah.
Yeah.
You're
Still.
So there's some computation there.
No. If
Mass
the
could be
masses
zero.
are different.
But even
Mass is 0.
but the v's themselves are also
Yeah, but
different.
you said MV.
The masses have to be squared. They have some.
Because they're not
Fine,
both
yeah,
M,
one.
they're
Okay,
They
one
have
and
some
two.
Yeah,
and they have to be
but I'm
different.
saying
It could happen because let's say
it can't-
these
no.
two in the first scenario, the in,
No.
for the
Yeah,
second
yeah.
scenario, the V is
we know this is true.
yeah okay.
We know this is true. They gave that to us. If this is true, can this be true?
It can because
No, it
because
can't.
the masses are
Because-
different.
No.
So even though the V's like okay, if you would say that the mass is the same, then it wouldn't make sense because you can't have V's equal the same thing as V squared.
No, but it would be no because the masses are different, and then so even if let's say if V1 was 1, which is the only case that it would work theoretically, then based on that, then M1 V1 squared would not be equal to M2 V2 squared. If the masses are different and you're squaring 1 in both cases, then that's not equal. So the first step wouldn't be right.
Exactly. The mass is staying the same, but you're squaring
okay,
that
okay,
other
okay.
one.
So you couldn't have
Okay.
But the masses are not changing step to step.
Right.
The masses are different here to here,
Right.
right? Like I'm not changing the mass from one step to the other. But I know for sure this step is right. Like I know for sure they guaranteed that for me, for sure.
We can literally prove that using like systems of equations.
You don't need to
There's
prove
like a
it, it's
mathematical way to
choice.
prove it though, right? Like that those two could not be equal. Like,
Just plug in numbers.
here- that's
That
not a
doesn't
very
prove.
rigorous proof.
Yeah, that doesn't prove this. How would you?
Proves
You
it
can
in one
isolate
scenario.
M1 in one of them,
Yeah, and then I can plug it in.
plug it in and rearrange it.
When
a
I
little bit.
rearrange it, what I'll
And if
probably
it-
end up getting is
If something is actually false, then
Something
you'll know
equals
that
0.
it's wrong, so it's-
I'll end up
You
getting
won't
something.
find one is one of the same. Because one could be squared.
I believe what you should end up getting is something equals 0.
Mass would also have to be 1.
Yeah, mass would probably equal 0. Even because math doesn't know.
Yeah, but
So
mass can't be 0.
what I'm thinking
Math
is
doesn't know.
that can't happen.
Yeah.
That cannot happen.
And if that can't happen,
Then D can.
so well,
Well, we
But
said
you
that the
could-
difference was
If
that
you can't-
I could have the same amount of force, but
Yeah.
maybe they're not over the same amount of time.
That's true.
oh wait,
The
because,
difference between B and D is that in B, I'm saying that they have the same time interval. They had the same amount of, or at least an amount of force over an amount of time, and whatever distribution they wanted. Here, I just said that I have the same amount of force. Maybe in one of them, it happened for 1 second. Maybe in another one, it happened for 20 seconds.
Yeah.
Whatever.
Work is changed energy, right?
Work is change in energy. That is true.
Maybe we could use.
Yeah.
But it's also
Would it be true if you said the one with the least mass has the greatest momentum?
no, it couldn't. Wouldn't it be the other way around? Wouldn't it be A?
Because you're saying that
Because-
V1 is a lot
Oh, wait.
smaller, so how can your momentum?
No, it would be A because when you do kinetic energy, right? In order for mv squared to in order for the kinetic energies to be equal
Right,
on
right.
both, then V in the one with a heavier mass needs to be
Yeah.
less by square root of 2 or square root of m, right?
Yeah,
We
so
can
it-
actually
it does
prove
make
how
sense.
much less it would be. Oh, sorry.
Yeah,
So
then when you
V2
take the square
would
root-
end up being a factor of square root m1 over m2.
Exactly. So then when you take the square root of V1 and V2, the difference is smaller. Like the velocities would have less of an impact. So the one with the greater mass would have the greater momentum. No?
Don't convince me, convince them.
That makes
If,
sense.
because in order for them to be equal in the other scenario, when you're squaring them,
Yes.
right? That means
The velocity.
that when you square them, the velocities are equal. Right?
Yes.
The
No.
They're
The,
not
the whole
equal.
term.
When
The
you square
velocity is not
velo-
equal.
sorry, when you
The
square
whole
velocities,
term is equal.
The terms are equal.
Yes.
So when you're not squaring the velocities,
Yeah.
the bigger mass will outweigh the smaller mass.
Yeah, that makes
Will
sense.
will have a bigger impact on it. Mass will have a bigger impact. When you're not squaring velocity, mass will have a bigger impact. There we go.
Yeah.
Because if I
Because
If you square-
the smaller mass needs to have a
In either case, the mass will have a bigger impact when velocity is not
is
being
not
squared.
squared
So you're saying
because when the
that
velocity is squared.
Yeah. Because
That makes
when
sense.
velocity is squared, they're equal.
I also that makes
I
sense.
can prove that D.
It also says
I don't
mass,
use elimination.
and the D doesn't have doesn't have to be
Yes.
true.
Wait,
Why?
and I can show you scenario. Like I can show you why D is wrong.
You don't have
Mathematically?
Don't
What?
have time.
Mathematically?
Yeah. Like because so F is MA, right? MA, right?
Yes.
So since the V V squared is different in each one, right? The
Yes.
acceleration has to be different for each one by a factor of like a square.
Well, no
Why?
time.
Because they could have
Not
they could
that
have
much time.
the same force applied over different time intervals.
And you don't
Yeah,
have time.
That was
Wait,
what we
does it
said
mean
was the
to-
difference
what does
between
it mean to
D.
accelerate a car, like to go from 0 to the next step above 0, or to get up to speed, because that's the difference.
To accelerate a car means to
To get-
change its velocity.
In this case, it means
Even
when
by
they
a
say
micro-
accelerate each car,
Yes.
it means to
Oh,
get
okay.
like from rest to the final thing.
So is it
you know?
from rest
To
to
a
final?
or to a value.
To any value.
To whatever
above
the
zero.
final value is signed.
No, no, no,
Like,
to any value
In this
above
goal,
0.
it's saying when the identical kinetic energy
No, no, no.
to
He's saying,
accelerate.
no, you're trying to explain something. He's saying something different. He's saying it's any value just above 0.
Oh no. The
No,
way this is
you're-
okay.
you're
I'm
accelerating
saying
from
what
rest.
acceleration is.
Yeah.
What
exactly.
they're saying is the amount of force was required to accelerate each car from rest to that
To
value.
the point
To
when
that-
the
yeah,
identical
to that value.
energy.
That's my question. All right.
Did you do the math for?
Yeah, but it comes something weird and I don't like it.
Does it give you?
Well,
Confidence.
I don't even want to. Like, it came up that the only way that those two things can be equal is if V1 and V2 are the same, but we already know that they're not.
Yeah. No, yeah.
That makes sense.
No, that's right. Because
But that doesn't make it. That doesn't make sense if M1 and M2 are not the same.
Exactly.
That's why I
Yes.
just wanted.
So that's what. But that's the difference
I'm
between
saying
physics
that-
and math. Like that's the interpretation. That's what we're doing.
But this is saying that because I set those two equations equal to each other, and the solutions were that V2 has to be 0 or V2 has to be V1. But if you put that back into
Yeah.
the two original equations, it doesn't make sense unless M1 and M2 are the same.
Which
But they're not.
Yeah.
So
So-
I don't know.
So
I
that's
don't,
wrong.
I don't know
No,
what this
that's
means.
But that's the point. There is no solution to that statement. There is no way to have your kinetic energy equal your momentum. I'm sorry. There is no way to say
You can't say that the kinetic energies are equal and masses are different.
And they're moments.
Yeah, then the momentums cannot.
there is no way to say those two equations.
Yeah.
You cannot make those two statements.
Where
When
and
where M is not equal.
When the m's are different and the
Yes.
v's are different. You can't do that.
Makes sense.
Aside from 0.
0.
Yeah. There's no way. Those are our.
Is
Those
a
are.
question like this supposed to take?
No, but I like the arguing. The arguing is really useful, and it's very interesting. In general, when I go through something like this, what's really nice is to go through. I try when I look at these guys, I try to find the one that I know for sure, especially in a multiple correct. I try to get the ones that I am very, very confident of. How do I get that out? Then the next thing I look for are the ones that I know cannot happen. So when I was answering this question, I honed in on C right away. Because I know if they have the same amount of kinetic energy, work is all about kinetic energy. It's all about energies, right? If I want it to stop, I want it to go to 0. I want them both to have the same amount of kinetic energy at the end anyways. Then I looked at B, and I realized there's no way B can happen because that velocity piece is different. Then it starts to slow down a little bit, right? The key part here is taking a look at
Acceleration.
Yeah, to get that guy, each of them, to accelerate to that velocity, you can't have the same force because they're going to different velocities.
Unless you know the time.
But you would. Never mind.
they would have to, in order to get to different velocities, right? I would either need them to have different times, or I'm not, and that's not what was implied. I would need to have different forces, which I don't have. That's not what was implied. We're gonna pick up on this guy, and I think what we're gonna do is play a little bit with some carts tomorrow. I think that's what we're gonna do.